Hello everybody, I'm Reinhold von Gleer, and we're in the shop tonight to turn iron into steel. This is the process of cementation, which is really a process of carburization, but cementation is the name of the process as it was developed in the late 16th century. Now, we say developed in the late 16th century because that's when we first have evidence. There was a treatise published in Prague, and at the end of the 16th century, it was commercialized with an operation in Nuremberg. And this quickly eclipses the period of focus of the SCA, but the process must have been known earlier on. The treatise was published in 1574, but it's really no different than what blacksmiths have been doing by the side of the forge since time immemorial, since the Roman age. But the explosion of learning in the Renaissance formalized the process of turning iron into steel and was what allowed the industrialization of steel production. So cementation is very simply placing iron in a carbon-rich environment. Carbon in iron seeks a kind of homeostasis, and ordinarily we experience that as decarburization. Young smiths will often experience decarburization of their work because they keep placing the work back in the forge to get it right, because they're not efficient with their metal shaping yet. And that's okay. It can be easily fixed by grinding. So we say forge thick, grind thin. That'll always remove your decarburization because carbon migrates in or out of steel at a rate of about 5/1000ths of an inch per hour. So not very fast, but very easy to ruin your surface if you aren't doing much stock removal. Now you can see here I'm just grinding and sifting the charcoal. Cementation was done with what they called cement powder or cementation powder, and that was more than just charcoal, but I wanted to demonstrate that we could do this with plain ordinary charcoal. And I'm also using plain ordinary steel from the hardware store. This is something that anybody can get, as is this piece of steel tubing. The process of cementation, when it was industrialized, was done inside stone coffins, stone vessels. They looked like coffins, looked like giant coffins. That's where they got their name. But it doesn't have to be stone. It doesn't have to be large. It can be done on small scale. However, it does take time. So at a rate of 5/1000ths of an inch per hour on 2-inch thick bars that were used in Sheffield, for instance, those furnaces had to run for a week. But here, with 1/8 inch parrot stock, you can, because you're going to have the carbon moving through the steel at from both sides. So 1/8 of an inch is 0.125. It's moving at a rate of 0.005 per hour. You can get halfway through in 12 hours. So that's what we're going to do. Also, the temperature at which the iron is cooking really makes a big difference. The rate of carbon migration at, say, 1400 to 1450 is about half of what it'll be at 1600 to 1625. So here we have my stack of parent stock, and I'm about to part off the coffin. And I've really been overly ambitious about how much material I would be able to fit in this coffin at any one time. Of course, I can fill it with that stack of steel, but I also need to fill it with a bunch of carbon powder, charcoal powder. And I didn't think about that when I cut up all of that steel. That's okay. I'm going to have a second baking later on. Now, since carbon migrates out of steel when it is in a low carbon environment, for instance, when it's just in a fire, and carbon migrates into steel when it's in a high carbon environment, for instance, when it's packed in charcoal or graphite. Graphite would be much easier to use, by the way. Then this coffin, since it is also steel, will also become a piece of high carbon steel. It'll be improved from the inside out. Now, this is the same kind of vessel that you would make if you were making canister Damascus, and a lot of makers will cut a plug instead of folding the edge over. It doesn't really make a difference. I always thought that the process of cutting a plug was a lot more cutting and fitting, but it welded up really nice. Ordinarily I would use a MIG for this, but the MIG machine was in a different area of the shop, so I was stuck with the TIG. And here, when the metal is all clean, it welded up beautifully. Even though I was just using a piece of baling wire as my filler material. However, when the coffin is full of charcoal, it got significantly more difficult to weld, and that MIG would have been really nice. Now, we're filling the canister with steel and charcoal. And the charcoal is, of course, a flammable material. If you've watched any YouTube blacksmiths making canister Damascus, you'll often see them drill a tiny little hole in one of the ends of the canister. And, well, when you have a flammable material, or just any gas that will expand when it's heated, inside a completely sealed container, well, you've just made a bomb. So we need to leave ourselves some space for those gases to release. And later on, you'll see when my canister really heats up, there's a tiny little torch that acts like a candle out of one end. Now, I was just using the gaps in the weld. Purposely left a few pieces unwelded that do just as well as drilling a hole. I didn't want to bother with drilling a hole with all of that carbon dust inside. But you can see it here where it spits and sparks, and you can even see a little flame erupt. And then you'll see that later when the canister heats up. Now, I mentioned at 1600 degrees, this process is going to take about 12 hours. So you need something that you can keep hot for about 12 hours. This is my heat treating oven, and it'll do the job just fine. But a pottery kiln will work equally fine. If you're working with fire, it's going to be a very difficult day-long process to keep your fire hot and your steel hot, so that your process of carbon migration doesn't stop on you. And here we get to see the big reveal. Lighting's not good. Here it is. Just the color difference alone, you can see there's been a significant change in the steel. And look how hard I'm pushing. I really cranked on that. As I pull these out, if you look at the bottom corner, you'll see a little shadow of blue, and that is where the charcoal fell away from the upper corners of the piece. Okay, that was the mild steel, and here, look at that. Look at that sparking difference. We've made steel. We're back in the shop with tonight's project. I'm Reinhold von Gleer, and what you're looking at is some of the steel we made last week. The bright colored steel is the steel that we created, high carbon steel from mild steel through the process of cementation or carburization. And what we have is the material for a Norwegian Seax. That's going to be tonight's project. And we'll see how far we get. The first thing we have to do is material prep. In this case, with surface prep. The steel has been sitting for about a week. We've got to make sure that it's bright and spotless so that our weld can be free from any potential contaminants. Even the untreated mild steel has to be sanded the same way. There we have the color difference. I think that's a nice little bit of contrast. Even though the steel looks clean, it still needs to be cleaned with acetone or rubbing alcohol, some kind of solvent. You'll see how much actually comes off the material that would have been contaminants inside the weld. You see? And now we're going to bind this up in preparation for the forge weld. I've got a little bit of baling wire here. And that is probably the most traditional method of adhering material together for a forge weld. But the problem is that baling wire now is kind of low quality. I've been struggling to find any kind of decent baling wire, and it snapped on me. So we're going to go with the old reliable, the MIG welder. You'll have to excuse the anachronism, but sometimes needs must. Now we're just going for tacking welds here. We're not trying to do anything fancy like a zero atmosphere weld. I did consider it, but I thought it would be more useful to show a weld with traditional flux. And here's our billet, our pattern billet, and here's a file as additional donor material. Now the file is very hard right now, so we're going to leave it in the fire for a little while and let it soften up. Here I'm using Iron Mountain forging flux, which I highly recommend. It's absolutely fantastic. There's the nice and hot file. We'll set that off to the side for a while. Come back to it later. I'm setting the weld. I'll be setting it a couple of times with light hammer blows on the anvil. It doesn't take a hard strike, and you can see the flux erupting out of the weld seams. That's a good sign. It's also necessary at this stage to keep the welds clean, just in case you might get any separation. You always want to do 3 welding steps, to tack, to set, and to blend. Or in this case, to set a little bit harder. I'm using the hydraulic press for the 3rd welding step. And in dealing with any kind of laminated material, you're going to want to work as hot as you can, especially if you have to work against the plane of the weld. And we'll get to that a little bit later, because that's exactly what we will be doing. I'm switching the plates out from a flattening plate to a fullering plate, and that'll let the drawing process go a little bit more quickly. You'll see that here. I think we got some pretty good movement out of that. But for the next step, we go back to the flattening plates, because we don't want to get our piece too distorted. And you can see here I'm starting to forge against the plane of the weld to draw out the length and to make sure that we don't get our billet too wide. Because ultimately what we want is some long square bars so that we can do our twists. The primary patterning in the migration era through the Viking Age was twisting. In fact, there are even Roman gladiuses that show a twisted pattern. We think this was probably incidental. Obviously, smiths did know that there was a pattern in the steel, and they pursued it. They wrote about it. They called it the serpent in the steel, among other poetic phrases. But we think that the twist was probably initially a proof of good construction, a proof of high-quality material, because with laminated material, which all primitive iron and steel was, if the forge weld was conducted improperly, or if there was too much impurity inside the metal, then twisting would reveal those flaws and open up the seams. So bars that were sold with twists were essentially proof of quality, and then those bars could be welded up with the twists intact, and that would appear in the steel. And it doesn't take long for an interesting artifact to become artistic. Right now I'm marking the middle point of our square billet. This is going to be the patterned billet. And I boomered the video. I lost that whole twisting segment, but what I'm showing you here is a shearing fracture, or at least what I thought was a potential shearing fracture in the twist. As soon as you begin a twisting process, there will be points on your twist that will go faster and some will go slower. And if you want a nice even twist, it's very difficult to work out artfully. So if something starts to over twist, the best thing that you can do is stop. But I didn't stop fast enough, and I'm pointing out that even though we forged that out, there's still a crack there. Yep. And I'm just going to go ahead and break that off. And we'll grind it down and we'll work with what we have left. If you ever have any kind of weld failure, the best thing to do is to grind it out, whether that's a failed lamination, whether that's a cold shut or an inclusion. Grind it out and start from clean metal, and just work with what you have. And now we're going to try the twist on the other side. So we're going back to that middle point that I marked, and using my twisting tool, we're going to be twisting in the opposite direction from what we had last time. Not that that was on video, but so you know. That way we can have a herringbone pattern in the steel eventually. And I think up here, yeah, you can begin. You can see the over twisting begin to start. So one of the things that you have to do if you're starting to over twist is either cool down that section or heat up the section that was under twisted, and that's what my brother, shop assistant, is doing right now. Also, twisting wrenches are notoriously finicky. They're really annoying to work with. Everyone has as good a solution as they can come up with, and none of them are really good. Here I'm going back to the original section, and I'm twisting in the opposite direction from what you saw. And I'm just going to try and tighten up that twist. Since my fractured section is no longer with us, we've ground that out. We're going to tighten up the twists that we have, and we'll see how evenly this divides. And you can see the middle point right there. I think it turned out pretty nice. Now we're going to forge that back down, because we do need square bars so that they can weld up on top of each other, and that's what we're doing right here. I think it came out very nice. I think here what I decided to do was make my squares actually a little bit rectangular, so that when I went to do the final forge weld, I had a little more surface area, and when I drew out the profile of the knife, I would have more room before I started distorting the twist. And here we can see the twist. It's not a very bold pattern right now, but that's okay. The pattern will increase in vividness once the material is hard. That has to do with the crystalline structure of the steel, which changes through heat treating. And right now we're going back to the file that we started with and set aside. Since we've taken the trouble to remove its heat treating, it's very much easier to grind down to flat. You don't have to flatten something like a file, but you risk cold shuts if you don't. So now we're on to making the blade steel portion of the knife. And again, this is some of the steel that we went through the cementation process with, the steel that we made into high carbon steel. And we have a little bit of known good donor material in the form of this was a Nicholson Black Diamond file. And that's a very period process, not necessarily using files as apparent material, but using known good and no longer necessary pieces of iron as a moderating factor when adding new steel. Because we don't know the characteristics of the steel that we made. It may be very high carbon steel, overly high carbon, or it might be medium carbon and not as much carbon as we need. Now, honestly, from the spark test, I think we have some really good stuff. But regardless, either way, the material of the file will be a moderating influence and should probably improve it one way or the other. So we're making a simple little billet here, and as soon as we get it all welded up, we'll toss it in the forge. No, we're back to the patterned material, and what we're actually going to do here is fold that over and begin to make the stack of the blade. So it's cut almost all the way through. And we'll just fold that over. And that's what we will be welding up. That was cut right on the transition point in between the two twist directions. You can, of course, do that hot. We did that while the metal was heating up. Again, I'm using black diamond forging flux, or excuse me, Iron Mountain forging flux. And I can't recommend this stuff enough. Compared to borax, there's no comparison. It's so much cleaner. It allows the welds to set so much easier. It's very difficult to explain how much easier it is to use this flux in comparison to borax, but you really ought to take a chance on it if you're doing any kind of welding in the forge at all. As you saw, I went ahead and I set the welds with a couple of heats on the anvil, and then I'm moving over to the forge. And those welds set very nicely. We've got a very contiguous material. And from here on, we're going to be forging in both directions, in the plane of the weld and perpendicular to the plane of the weld. And that means those seams are very likely to want to open up. So we're going to have to be careful with that. We're going to have to work hot. We're going to have to work carefully. We're probably going to have to reflux a number of times. Here I've got the fullering die on the billet, and I'm forging both ways. And I did see the seams on just the very edge start to open up, but no, it came out very nicely. We were able to get a very nice, clean billet, and here they are. Here are our 3 pieces of parent metal, and next we're going to try and forge a Seax. Tonight we're going to weld a knife out of the steel that we had created, out of the little billets. First, we're going to break apart the fold that we had made last week. If we had proceeded straight on to welding up the billets from the bars that we made last week, that fold would have been perfect. But as it is, it's had a week to sit and oxidize, and we're going to have to improve the surface. And that's what we're going to start doing right now. Now, there's a couple of times where I'm going to hold the bars to the camera and show you the surface finish. And what I'm trying to do is show the visible layering to the camera, but I'm afraid that wasn't picked up very well by the camera. But the layers in the steel are very visible to the naked eye. Every imperfection that you can see there is a barrier to a successful weld. So we have to get that all off. We have to make our potential weld surfaces as clean and as friendly to a diffusion weld as we possibly can. Otherwise, there's just going to be a lot of failures, a lot of inclusions, a lot of striations, which is very common in artifacts from the medieval period, but that's not what we're going for. Now we have our bars fitted tightly together, it's time to trim them up. You'll notice each one is a different length, and that's purely by accident. It's absolutely possible to work with different length stock and weld up a successful blade, but not to get the blade that we're looking for. We're going for a Norse Seax, specifically a Norwegian Seax this time. And in order to get the herringbone pattern down the spine of the blade, we have to have our bars nearly the same length. There's actually a little bit we can do to work with different lengths because of the way the blade will be bent to shape. But you'll see that a little bit later. Now I'm welding up the stack. I'm only doing in tacking. Again, I'm not doing anything fancy like a zero atmosphere weld. Although that would probably make the weld more successful, it does make the process less illustrative for historically minded smiths. So what we're going to be working with is the situation that historic smiths were working with, where every weld seam had to be carefully monitored. And that'll be important later on. The forge I work with is a Chile forge. I'm very happy with it. There are a number of YouTube blacksmiths who are working with Chile forges, and I think their burners are just the best in the business. For Venturi burners, forced air burners are a different animal, and of course, those are much more powerful. But for the Venturi process, especially for a beginner to intermediate smith, I can't recommend Chile forge enough. I'm using light hammer blows to weld up the stack, and as I've said before, every weld step should be performed 3 times. First to tack, then to set, and then to blend. We're setting the welds. And the reason for that is because of the mechanics of diffusion welding. All fire welding, all forge welding is a species of diffusion weld. And diffusion welds happen when the atomic surface, or the atoms of the different surfaces, diffuse and mingle together to such an extent that there's no longer any difference between the two surfaces. And that's really a function of heat and pressure and time. Now we're over at the hydraulic press, and for tonight's project I'm only going to use the press for drawing out. Where a historic smith would have had the assistance of a striker, I'm going to use the press, but for everything else I'll be working on the anvil, and you'll see that. I'm using a very gentle fullering die here, and I'm doing that for a couple of reasons. A fullering die is exactly what you need to draw out your piece, draw the length out of your piece. But the fullering die you may have seen in previous videos is much more aggressive, and right now we're working perpendicular to the plane of the weld. As I've mentioned in previous videos, that's the most stressful thing that you can do on your welds. So you want to make sure that your process is gentle, and you want to make sure that you go back to the anvil and reset those welds, because again, diffusion welds is a function of pressure, heat, and time to allow those surfaces to intermingle. And if you have pressure in the opposite direction, away from the plane of the weld, you can pop those diffusion welds apart. And that happens very easily in smithing, especially with fairly primitive steels. And historic construction techniques. Modern knife smithing techniques have completely eliminated a lot of these stresses from the process, but that's not the objective. You can't get historic results without at least a few historic techniques. So we're going to be drawing out gently with a gently curved die. You might say, well, why not just use 2 flat dies? And that is more gentle on the welds, but actually the sharp faces of my flat dies will cause bumps and ridges inside the or on the face of my surface, and can cause cold shots. That's really just a function of how those dies were made. But they're very good dies. Now we are back to the flat dies, and we're drawing out in the opposite direction. We're drawing out with the planes of the welds, and we're going to make sure that our billet is nice and flat and straight, so that our pattern is nice and flat and straight. And you'll see me reflux many times throughout this project, because, well, maintaining those weld seams is very important. and you'll see why later on. Now, we're just about to start tapering the primary bevel of the blade, and we'll be working on this for quite a while because we're doing it all by hand with this bar construction. Tapering the knife by hand is absolutely the safest way to go. I would not want a chance doing this with mechanical assistance. It's just way too likely that those welds will pop apart. Something that you can do with hand hammering is drive. You're not hammering straight down. You're hammering the work back into itself. So there's much less stress against those diffusion welds. You're much less likely to pop them apart. And ultimately, I will pop the edge of one of these welds apart, and you'll see that here in a minute. But if you work trying to get additional width out of your billet at this stage, because this is the wrong stage to get additional width out of the billet. You will, because you're reducing its cross section. But if you try and draw it out, like with a fuller, going the opposite direction, or with a cross peen, you'll pop those welds apart very quickly, and it'll be ugly, and then you'll have a heck of a time trying to drive it back together. So almost every other step, I'm working to reset and reseat those welds, and then flipping over to work on that bevel. And it's a process. You can only have admiration for historic smiths and how carefully they had to husband their work, and how callous they might have to be to sacrifice it when it had gone wrong. Now, here in the beveling process, I'm hitting a lot harder than you've probably seen me working before. You want a lot of energy put into this. You want to strike from the shoulder. You don't want to strike from the wrist or from the elbow. Your arms will thank you later. Trust me on that. But also, the more energy that you deliver, not straight down, we're actually going a little bit sideways. We're driving the material back into itself, and that's going to put a lot less stress on those diffusion welds. It's a little bit later, the piece is cooler. I'm really happy with how that first beveling has come out. And now it's time to take off the front little bit of the weld. The edges, the ends of welds are never very good material, so you want to get rid of them. We're going to mark that out and take it over to the grinder. Of course, you can do that hot. You can use a hot cut, and that was done in period. However, you get, depending on how you build the shape of your hot cut, you can wind up with a lot of pattern distortion. It can be actually very ugly on the end of your knife. The way to prevent that is to have a hot cut that is only beveled on one side, and I've actually worked with building one of those, but it's not done yet, so I'm not going to do that process hot. But you can. Here we're rolling over the end of the knife and turning the bottom of the knife into the center of the knife. And that way the pattern on the blade will flow much more fluidly. We do see that in Norse construction Seaxes, in drop point knives, drop point and clip point Seaxes. We see that. Not so much on Anglo-Saxon blades. The although there was much variety in Anglo-Saxon blades. But the broken back Seax, you typically see the blade, the bit of the blade, only running along the bottom, and the pattern truncated with the clip on the top. Now here I'm back to beveling the blade, and I have a hardy tool that I'm setting the back of the blade against to aid in making sure that there's less stress on those welds, but something has gone wrong, and we have a delamination developing. So you flux it up, you see if you can set it back together. It'll work for a little while, but the same stresses that pulled it apart are going to keep pulling it apart because I'm not doing anything different. Ultimately, if you have a seam that fails, the best thing to do is to cut it off and work with a smaller billet. And that's exactly what I wind up doing. I think I do that off screen, but I'll be chasing this seam around for a little while. I think here I've just cut it off. And it behaves nicely for the rest of the build process. I lost about a half an inch. But that's okay. We have plenty of metal to deal with. We'll have a very nice, healthy sized blade. But it's only illustrative. If I, in a modern shop, am dealing with this, our predecessors, how much more did they have to chase the same problems? And how much more worthy were their results? It's really impressive when you think about it. Here, I think I'm paranoid of having another seam open on me, so I'm doing as much work on the bottom of the blade as I am on the side of the blade. But it worked out well. I didn't get any more seams opening up. I'm getting to be really happy with the shape of that blade. I'd like it to be a little bit more drop pointed, but this is perfectly within historical parameters. Now I think I'm paranoid of opening up seams inside the blade billet. That ultimately didn't happen, but who knows? An ounce of prevention is better than a pound of cure. Now, since I'm happy with the shape of the blade, it's time to start working on the tang. And that bar I've been holding with breaks off very easily, and we'll move over to tongs. And the first thing we have to do is portion off a section of the material to become the tang. And I'm doing that with the hydraulic press. I'm using the two flattening dies to act as a hot set. The way that you would do that operation in historic times is with an assistant. The smith would hold a hot set, which looks like a hammer that has very sharp edges, and the edge of the anvil, and the assistant would strike, and you'd portion off that material. And then, of course, the rest of it can be worked by hand with a hammer, which is exactly what I'm doing. There are tools called guillotine tools that will allow a smith working alone to isolate material the same way. But guillotine tools were invented in the United States. They're really not historic, although they are hand tools. The tangs of Seaxes, not uniquely, but certainly unusually to modernize, are only partial tangs. They'll only go a portion of the way through the handle. But you need to make sure that any partial tang you do will at least sit under the middle of the hand. If the tang doesn't sit at least in the middle of the hand in use, and it's a cutting knife, A stabbing blade is a little bit different, but a cutting blade that doesn't sit under at least the ring finger is going to break out of the handle in use. So you need to make sure that your tang is at least long enough to do that. And this one is. We've got 5 inches of material there. It'll be just fine. But it's something to keep in mind when working with historic blade types. And I think this particular blade just turned out beautifully. I'm very happy with it. Beautiful pattern welded Norwegian Seax blade. Although you can't see the pattern as it is right now. It's covered in fire scale. Fire scale is, well, it's one of the mechanisms of decarburization, actually. And it's very abrasive. It's hard on your files. It's hard on your grinding belts. And what I like to do is dissolve it away using ordinary household white vinegar. Now, obviously, that's not something you can do if you're in a hurry, but if you have the time to let it soak overnight, and I do, then by the time you come back in the morning, all of that pesky fire scale will have been dissolved away, and you'll wind up with a nice, clean knife blade that you can begin to work on. That's exactly what we're going to do. I'm using a magnet because I'm a blacksmith. I have cuts all over my hands, and vinegar is kind of painful. But I think our blade turned out beautifully, and you can actually see some of the patterns in the steel right now. I'll point them out to the camera. You can kind of see it on this side, but on this side I think it's much clearer. So you can see where our pattern will be exposed. Right now I'm just taking it over to the wire buffing wheel and knocking all of the remnants of that fire scale off. You do need to be careful about wire wheels and buffing wheels. They can grab and throw tools almost at the speed of light. But they do leave a nice finish. I'm very pleased with that as a rough forged finish. But we're going to have to take it a lot further than that. But I do want to show you something. I'm dipping the blade into ferric chloride. Ferric chloride is the most common etching acid to reveal the patterns of the blade. But do you see a pattern? I don't. We know it's there. We'll get back to that a little bit later. What I'm doing now is I'm straightening the blade on the anvil. Obviously, you can't do this to a hardened blade. Well, actually you can if you're careful. But the blade is not hardened right now. So the little S turns and all of the imperfections in shaping. It's a necessary or natural part of working with a steel when it's hot. You can take that out when it's cold. Now, if you just jumped straight to the grinder, you can also take a lot of that out with abrasion. And we do say forge thick and grind thin, but that's not what we want to do right now. And here I'm trimming up the perimeter, and I want to clean up one side of the blade. Now later on I'm going to be doing all of the shaping of this knife by hand with files, but first I want to take the opportunity to show you something interesting. We made the steel of this knife by surrounding iron bars in carbon and holding it in high temperature long enough that the carbon could soak into the blade, or into the iron, and make steel. We made steel from iron, but the carbon can flee and make iron out of steel just as easily. Now, we've been here before with the ferric chloride, and you saw that there was no pattern on the blade, even though we know it's in there. So, as you can see, there's nothing. But when we flip it over, suddenly There's a pattern. Now, it is very faint, that's true, but you can clearly see that there's such a difference between the surface as it was forged and the surface as it was ground. And that's because the process of decarburization has left the surface of the knife as it was rough forged as nearly pure iron. We can make steel with carburization, and we can make iron with decarburization. Our ancestors were not ignorant of that either. In the Eddas, the Norse writers will talk about the serpent within the steel. And that's very true. That's literally true. Because the serpent is not on the surface of the steel, not as it comes out of the fire. They have to go in and get it with files and grindstones. And there's going to be a lot of filing here. What I'm doing mostly is draw filing. I think that's probably the most efficient way of removing stock with a file. But sometimes I'll go at it from the side. And I do want to alter my scratch lines so I can see where I've been. This is a perfectly fine way of doing your stock removal. And I can see the patterns so clearly as I'm going at it with a file. But unfortunately, it doesn't translate very well onto camera. I've tried from a couple of different angles using different light sources, and you just can't see it here on screen. But trust me, with the naked eye, it's very visible. And it will be more visible as I refine the surface, and especially as we go at it with acid. Here I've been at this filing for, half hour, 45 minutes. My shoulders are getting really tired, I'll tell you that. I've taken a couple of breaks. Here I'm going ahead and I'm revealing that pattern. It pops up so quickly with ferric chloride. There are other acids that will do a similar job, but nothing so neatly and beautifully. I'm really happy with this herringbone pattern. It is very faint on camera right now, I know. It will darken once we harden it, which won't be... you won't see the result on this video, but we will go ahead and do the heat treating step tonight. More filing, more filing. It's a good workout. I work up a sweat. And this is not necessarily exactly how our ancestors would have done this. They had grindstones. They had grinders. Now, in the Norse period, I'm not exactly sure what metal shaping would have looked like. The Romans, when they were given gifts from Germanic smiths, were very impressed with their ironwork, but they said they did not use files at all. They merely did such advanced forge work that they said you would think that the blade had been made with files and not with hammers. But I don't have records of what Scandinavian smiths were using. I know they did have files, so presumably they were filing to finish. But grindstones were just as well known. Metal scraping, using essentially a plane. It's a metal plane. Can remove a shocking amount of material, and we'll probably try that on a future project. Right now, we're going through a normalization step. Because even though we straightened the blade, there's still stresses in the steel. And they have to come out. Otherwise, when you do your hardening step, you'll wind up with a banana. Better. Still a few problems, but we're getting there. There are a number of ways to take any bends and twists out of a blade. You can do it at several different times during your process. You can do it during tempering. You can do it immediately after hardening, before tempering. I like to do it right here. The blade is soft. The hammer blows. Each hammer blow does add stress to the blade, and so every time that you straighten, you need to normalize afterwards. But you should be doing several normalization steps anyway. Normalization is more or less hitting a reset button on the structure of the steel. It's raising the steel to critical temperature, which is almost where the steel begins to glow. It's not quite the same temperature, but they're very, very close. So you make the steel glow, and a lot of the stresses come out of the steel. But those stresses that were there will be acting on the blade as it comes up to temperature, and as you bring it out of the forge, you'll see what you missed. And so you do it again. It's good practice for every blade to go through 3 normalization cycles, but this one I think will need a few more. Finally. Yes, that's perfect. I'm really happy with this. I hope that wasn't as exhausting for you as it was for me, but that was satisfying. Now that the blade is straight out of normalization, we can heat treat with confidence. Obviously, some things can still go wrong. Unexpected things will always happen in a heat treat, but you can increase your chances by making sure that your workpiece is heated as evenly as possible. I've finally gone ahead and invested in an oven, which helps that an awful lot. But even when you're flame tempering, if you take a piece of pipe and let the pipe be exposed to the heat and use your workpiece, let your workpiece be heated inside the pipe, you can get a very nice even heat. We're quenching into, it's a fast quench oil. I use Huda-Quench. It's analogous to Parks 50, and both of those fast quench oils are analogous to a water quench. They're just a little bit safer on your result, and I'm very happy with this result. You can even see it in the camera. It's dead straight. No warping at all. And there's the file skating off of that edge. That's great. Now, every hard blade needs to be tempered. The stress needs to be relieved. We did a good job of getting a lot of the stresses out of the blade during the normalization process, but hardening causes its own. And it's rare, but it has happened that a blade that's left hardened will, and just sat out in the air, will snap and destroy itself because of the stresses, the internal stresses that the hardening process is created. So you always want to temper, at least do a preliminary tempering right after hardening as soon as possible. Now, the heat treating oven would be perfect for tempering, but right now it's very hot, hot enough to harden the blade. So instead, we're going to go over to the vise and use a torch. We're not even going to bring this up to a straw color. We're just going to begin relieving some of the stresses in the steel so that I don't have to worry about it shattering if I were to drop it. That has happened. But that's all we're doing. We're just making sure that the blade is safe to handle. Nothing's changed. It's still straight. You can see the pattern in the steel. We'll be able to see it much more clearly soon. But not tonight. It's been a long night. I think that's enough for now. We'll pop it in the kiln, and I think we have a beautiful result for one night. Here is the knife as we left it, right out of heat treat. It's looking gorgeous and hard right out of its tempering. And today we are going to be bringing a blade out of this beautiful blade-shaped piece of steel. Now, we could go over to the belt grinder and spend about 20 minutes pulling a beautiful sharp blade out of this lovely piece of steel that we've been working so hard on. But we went to the trouble of carburizing steel out of iron. We went to the trouble of folding and twisting period-accurate billets, so it wouldn't be very medieval of us to hop on over to the belt grinder. So we're going to grind the blade the way early medieval smiths ground theirs, by hand. There will be a lot of hand sanding and hand grinding in this video, and partly because that was the medieval experience. I sat down and I wanted to make sure that this blade from start to finish was as authentic as we could make it in a modern shop. So I sat here for hours and hours and hours, and I'll spare you all of that. Sanding away and grinding away later on stones. And again, partly that's because that was the medieval experience. But also because I'm a blacksmith who recreates the early Renaissance, doing something from the early Middle Ages, and there were a few gaps in my historical knowledge. Because when I sat down, I said, well, they had files. We know that from the Mastermeyer chest. And they had grindstones, handstones. We find those everywhere. Sanding and sharpening stones are, even from the Dark Ages, are still commonly sold today. But I thought to myself, no, the grindstone, the rotary grindstone, is out of period. It must be. And that was almost right. The rotary grindstone was not known in Scandinavia until a bit later. However, the earliest depiction of the rotary grindstone, and it had a hand crank, was from the Utrecht Psalter in Belgium. It was Carolingian. It was penned in about 830. That's about 30 years after the death of Charlemagne himself. So we're well into the Carolingian dynasty at that point. And we're well into the Viking Age. That is typically pegged at about 770 when the Viking Age kicks off. So if I'd taken a rotary grindstone, and I actually have a broken rotary grindstone, and that's a project for probably another year, it would have been authentic to work on that. But I did all of this with handwork. And here you can see I've gone over to some flat stones, coarse stones, and I'm thicknessing the edge of the blade, getting that really towards an edge. I don't actually want a very sharp blade because it hasn't been assembled yet, but I get it down to about 1/4 of a millimeter is where I'll stop with the sharpening of this blade. Now we know there was an awful lot of sharpening done on large stones because we can see the tracks in those large stones, large finely grained sandstones, from where many, many knives were sharpened and really shaped. Sharpening doesn't take too much wear out of a stone, but grinding a blade certainly does. And some of the stones that have been recovered have deep tracks, very deep tracks, where hundreds of edged implements have been sharpened and ground away on those stones over decades, centuries. I mean, stones are stones. Over here, we're testing the hardness of the blade, and these are hardness files, hardness testing files from Japan. And this is the first of those files where there are a few places that the file skips off the blade and a few places where the file bites. And so about 55 Rockwell is right about where the file starts to bite. And that's a very respectable hardness. Would have been seen as an excellent quality knife in the Middle Ages. Unfortunately, we're back to sanding again after having been on the stone. The stone moved more material than the sandpaper, but we want to make sure that there is a very nice finish because we are going to etch the blade. It's going to be pretty. I'm getting it pretty, but it is a process. Every stage of the knife-making process is satisfying because the blade, the object in the physical world, is getting closer and closer to something that had only existed in your imagination. And I love the blade right after it's been finished. It looks so satisfying. Right now, we're going to dip it into ferric chloride, or a ferric chloride and water mixture, and take a sneak peek at what the design looks like. And we've only left it in for maybe 5 to 10 seconds. But the pattern is gorgeous. I'm so happy with how that turned out. That's exactly the herringbone pattern that was what we were looking for through this process. The darker steel is it is dark because of the material of the file that we included in the blade billet. And the two colors on the spine are made from the steel, the mild steel that we started with, and then the high carbon steel that we created through the process of carburization many videos ago. Now we're going to go ahead and put it in a full etch. So we start off by cleaning off the blade, and then degreasing it and making sure that any oils or sediment is completely off the blade. We use acetone for that. It's so nice. Very happy with this. And then we go ahead and we put it in ferric chloride. So we're going to go back to our little piece of stainless pipe. We're definitely putting on goggles. And then for this we're going to use straight ferric chloride. We have about 1 gallon. And that'll be enough to cover the blade. We'll go ahead and drop our knife in carefully. And then we're going to leave it. We will leave the knife for about 4 hours. And that'll be a very nice deep etch. Four hours is a good etching time for a blade like this. That's enough that each layer is able to get some distinct topography. The types of steel that are more resistant to the acid will be a little bit raised. The types that are less resistant will be a little bit recessed. And that will be enough that even if you buff the color out of the steel, you'll still be able to see the pattern because of the microstructure. And here it is. Weeks of work. It's gorgeous. Very proud of this. This will be going off to a friend who will put a suitable handle and sheath together for it. Thank you for joining us along this process.
Thank you for checking out my YouTube channel. If you enjoyed this video and would like to watch more of my videos, please follow the links on the left-hand side. Remember to select thumbs up that you like the video. It helps with the algorithm. If you have any questions or comments, please post them below. And please click subscribe and ring that bell to be updated when new videos come out.